Maarten Mulders. I work at a Dutch company called InfoSupport. We mainly do consulting. We do data science. Actually, since before it was a hipster thingy, we already did that. But today's talk is mainly about software engineering and architecture. And to make sure that we're on the same topic, I would like you to raise your hand. Great. Because I assume that everyone has at least one insurance policy at home, right? If you don't, you can drop your hand. Okay? If you have 2 of them, you can keep your hand raised. Otherwise, please drop. 3 of them. 4 of them. 5 of them. Okay. I can figure who's Dutch. Because in the Netherlands, people tend to have a lot of insurance policies. Like, really a lot. We say that we are insured from the cradle to the grave, and that's quite literally true. There are around 7 million households in the Netherlands, and around 99.9% of them is insured with at least a couple of insurance policies. And yet, for Dutch households, there is no way to see in one overview what kind of insurance policies you have. You need to look it up. You can go to the portal of your insurer and you'll see, for example, oh, I have a car insurance here. And then you go to the web portal of another insurance company and you can see, oh, I have my contents insurance here. But there's not a single place where you can see all insurance policies that you own in one overview. And since there are around 400 companies in the Netherlands that can somehow sell insurance policies, it can be quite a struggle to find them all if you forgot about one. And to tackle that, the idea was born to create an online portal where you could easily log in, make yourself known, and then you would see all the insurance policies that you have in one view. Well, great idea. And maybe we all know this feeling of customers walking in at your office and saying, I have this brilliant idea, can you build it for me? After all, you're the software company, you can build stuff for me. So they came in with this, and they said, can you build it for us? We said, yeah, sure, it's not that hard. A bit of UI, a bit of data, no problem. Oh, but by the way, it's responsive, right? It does work on a mobile phone, okay? Yeah, sure, we can still build that, that's no problem. Oh, and that's great, but there's a couple more things. It must also be scalable. Scalable, okay, what do you mean? Oh, we'll get to that later. Okay, it must be secure. Okay, I can understand that because it's all about financial data. And if, for example, I can see that somebody else has a content insurance policy which covers like 5 million, then probably this person thinks he's rich. And if I know he's rich and I know he's away from home, and I'm a burglar, I have a job to do. But there's a little trick there. We can't actually store this data because, well, you know, it's sensitive and the companies that own the data don't want to have it stored anywhere else than in their own back office systems. So it must be retrieved in real time. Is that possible? Yeah, probably. And there are 400 of them. And that's where we felt silent for a moment and then said, okay, so just to make things clear, we have around 7 million households, we have one system, and we have 400 backend systems. Is that right? Yeah, that's right. That's what we need. Okay. Challenge accepted. We're going to build this. Well, and good architects as we are, we started to build something simple, because simplicity is always a good thing. I think you've heard enough of that yesterday morning. Start as simple as possible. David Wheeler once said not exactly this, but it covers quite much what our first approach was. All problems in computer science can be solved by another abstraction layer. Not exactly David Wheeler, but that doesn't really matter because that's what we thought was a good solution to this problem. Let's just move the problem away. So we have a couple of systems in the top that will render the user interface, that will make sure that everything is secure and so on and so forth. We'll create some kind of a routing engine there, and then we'll have all these insurance companies, and they will deliver the data to us. And this routing engine will have the responsibility to retrieve all the data in real time, given a consumer is logged in to the system. It will check with all the insurance companies, do you have any data, do you have any data? And there's one thing, you would get some kind of a code from your insurer that allows you to retrieve the data from that company. And somewhere in that code is also a part that identifies which insurer it involves. So, well, this routing engine can be pretty simple. You read the code, you pick out the part that says it's this insurance company, you contact the right insurance company, you say, give me the data that belongs to this code, you get back some data, and you return that to the main systems. Shouldn't be so hard, right? So we fired up the IDEs, we started coding. Luckily enough for us, there was a standardized interface, so we didn't have to write 400 different adapters for that. We made a convention that every insurance company was allowed to have exactly one address where we would contact them for getting the data. And this linking code, as I said, it includes the insurer ID, so we could quite easily route the traffic to the right insurer. We decided to go with Spring Boot because we had other components in the solution that also worked with Spring Boot. It worked quite well, delivered a great productivity. So let's just go and see where things happen. Shouldn't be so hard after all, right? Well, we coded for a week or two or maybe 3, I don't know exactly, and then it was done. Great. So we asked ourselves the question, will it break? I mean, 7 million households, maybe for Spain it's not that much, but for the Netherlands it's quite a lot. And yeah, we wanted to put this system under pressure and see what would happen. Would it break? Would it blend? Would it disassemble? We didn't know. So we wrote a simple script, and this script would execute 2 scenarios, a simple scenario with just simple business logic, and it would execute that quite a lot of times, and it would in parallel execute another script, another scenario, which involved a bit more complex business logic, and well, we would just add some users every second and see where it goes. We wrote the script using Gatling, because if you use Gatling you get nice reports out of the box, and the reports were really nice, except it did not exactly display what we hoped for. As you can see, almost all traffic failed. And if you look at the table with the most occurring error messages, it says too many open files in system. Okay, need to figure out what it is. Let's look further into the report. Okay, well, what do we see here? This is the response time in milliseconds, 50K. 50K, that's 50 seconds, that's quite a lot. This is over time, so it's just a couple of minutes. That's the number of users. And there it drops. All traffic completely drops. But we had a script that would run for 10 minutes, so what happened? I'll save you all the time we spent into analysis, and let's dive just straight into the conclusions. Okay, it breaks. This is quite easily to see. We did blocking network calls, first of all, which is, well, not very good idea in this scenario. We didn't configure anything of a timeout. And that is quite a thing, since we had a couple of dummy insurance companies built, and they had varying response times. Most of them would respond within 1 or 2 seconds, 0 or 1 second, somewhere between 0 and 1 second. And some of them would randomly explode into 2 or 3 seconds. But we did not have a timeout, so we would just wait for 3 seconds if that happened to be the case. So within 1 minute or something like that, the whole JVM is just waiting for network traffic to come back after we send a request. This doesn't scale. Actually, this doesn't even work. And while we were analyzing, we found something else. We found out that if one of these dummies would crash, because they did, we would still try to contact it. It wouldn't respond, obviously, because it was down, but the system would try to connect and would wait for, I don't know, 30 seconds, and then come to the conclusion that there was a connection timeout. So, not sure if it's related, but it is an issue, and it will slow down the system even further. And there we had at least a few things that we needed to tackle if we wanted this to be a great success. It's time for a little excursus. Please raise hands. Who of you does know the Reactive Manifesto? I don't see too many hands, so let's go for it. The Reactive Manifesto is often pictured like this. We see 4 concepts. Message-driven is at the bottom. It has arrows to elastic and to resilient. There's an arrow straight to responsive over there on the top. And there's a bidirectional arrow between elastic and resilient. Let's go through these concepts. First of all, message-driven, which is at the bottom of the picture. A reactive system, says the manifesto, does rely on asynchronous message passing. And this message passing establishes a boundary between components that ensures loose coupling, isolation of components, and even location transparency. The second concept is elastic. It's there on the left, and it's enabled by being message-driven. The system stays responsive under varying workload. So a reactive system can react to changes in the input rate by allocating more or less resources. Okay, great. On the right, there's resilient. And being resilient means that your system is responsive, even in the face of a failure. And to do that, you must contain a failure inside each component so that parts of the system can actually fail and recover without the whole system being compromised. And that property is also enabled by being message-driven. And then on the top there's responsive, and being responsive is all about giving an answer and giving an answer quickly. So we prefer to give an error instead of waiting very long and then giving some data. Or maybe even better, say something like, okay, we're working on it, hold tight, your data will arrive soon. So this manifesto actually covers all the things that we need if we want this routing engine to be a success. But then again, how are we going to build this? Because these concepts are nice, but I haven't seen a single line of code yet. And is there actually any toolkit or framework or language that I can use to build systems like these? The concepts are great, and I can easily see that they fit my problem. But how do I build it? And that's where we met the actor model. Not to be confused with models in movies and so on and so forth. The actor model. And the actor model isn't something new. It was designed by Carl Hewitt in 1973. That's even before I was born, actually. And yet, this model quite nicely fits into this reactive manifesto that we saw just a minute ago. What does it look like? The actor model is all about actors. It's this big circle over there. The actor is supervised by a parent actor, which instantiated it and which will supervise whether this actor is still in a good state, still healthy. This actor can have some state which is private to itself. Nobody else can access it. There's no getter methods for the state. There's no method to get a tiny bit out of it. there's actually no method at all on the actor, because actors communicate to each other using messages. Remember the message driven at the bottom of the Reactive Manifesto? That are those messages. They arrive in a mailbox, and when the actor is ready to do some processing, it will pick the first message from the mailbox, and will start to process it using its own processing logic. And this processing logic can obviously do a lot of things, but it's what is very important is that this actor thinks that it lives in a single-threaded way. It's called the single-threaded illusion. It thinks it's the only one in the world when it comes to threads being run on the machine. That's not true. There are a lot of threads running on the machine, and if you run any Java application and you do a thread dump, you can easily see that for yourself. But inside this actor, it will think that there are no other threads running in the machine. So it can easily do things without having to synchronize on a lock or something, because who needs locking if there's nobody going to steal it? I don't need a lock. But on the other hand, the actor is not allowed to do any heavy processing itself. It can do the processing, but if there's heavy lifting involved, blocking network calls, for example, or heavy computations, or something that can easily go wrong, that's error prone, the idea is that you offload the work to a child actor. You can give birth to the child actor, give it some kind of work, using a message, obviously, again, and the child actor will do its work, and it will succeed and send you the result back using another message, or it might crash. But since you're the parent of the child, you can supervise it, and you know it will have crashed, and you know that you need to do some kind of fallback. And you can easily have a lot of child actors, and you easily delegate work to all of them, and they will do the work for you and get back the results. And as you can see in this picture, one actor is no actor as they come in systems. If you have just one actor, that doesn't make sense. The power is in the fact that there are a lot of them, and that they cooperate together to achieve some common goal. Now, we took a whiteboard and we started to draw, because this all sounded amazing to us, and we were like, this is definitely going to solve our problem. And we finally came up with this picture, and it might be impressive, so I'll just let you look at it for a second, and we'll walk through it, and we'll see that it covers most of the requirements that we have for our solution. At the top is an actor that just gets all the incoming requests from the main systems. They communicate with each other over HTTP, so it's called the incoming HTTP actor. It's not very original, but well, you have to find a name for it. A request comes in, and it sends a response back. Nothing too special there. That's how even serverless work. It can then delegate work to the retrieve policy data actor using a retrieval request. And this retrieval request includes all the data that's needed to get the actual data from the insurance company. Well, this actor, the first thing it does is it sends a message to itself. Not immediately, but it schedules the message to be sent in, for example, 2 seconds. And the message is called a retrieval timeout. Remember that I said we had no timeouts in the first solution. That's how we fixed it. We just said, okay, once I start to do my work, I need to remind myself in 2 seconds, I don't want to wait any longer. Okay, having said that, I can offload the rest of the work to this actor in the middle and say, go do your thing, get me the data. It will then split the request and see which individual insurance companies need to be contacted. It will create a new actor for that, and it lives just to make a request to that insurance company, and after that it will die. More, it's metaphorically, obviously. So it sends a message, retrieves some policy data for me, here's the linking code to be used, and this actor will then finally use the interface that I talked about earlier, the standardized interface, to contact either insurer A or insurer B, send the request. I don't know how long it will take before a response comes in, but it doesn't matter. I can wait for a very long time. It doesn't matter, because the request will come back as the response will come back as a message itself. So this actor will receive a message, retrieve some data for me, will then send a message to the external system, and the external system will send the response back as a message itself. The HTTP client that we are using in this solution is itself also actor-based. So the response is a message. And that means that this actor doesn't have to block or wait or whatsoever. Then, if anything gets back, be it an error or be it some kind of useful data, it will send a message to this actor here in the middle that lives for the whole lifetime of the system, and it just collects some statistics. Because we wanted to make sure that we could deliver reports about the performance of the external systems. Like this insurance company has a good backend system. It returns data very quickly. It's almost never down. And this other one, well, I got a failure, so I'll write down. Once again, it failed connecting to this insurance company. Well, these actors send back their data or their failures to the main actor, and if that actor didn't receive its own timeout already, it will just happily collect the data and then send it back to the main actor, which will transform it in some kind of HTTP response and send it back to the client up there. And using this diagram, we had almost all properties in our solution that we wanted to have. But remember the little side note that I mentioned. If one of the external systems is down, we will still try to contact it. And we didn't tackle that problem yet, because we will still do that in this solution. So we need another pattern to solve that. And that pattern is called the circuit breaker. Circuit breaker is a very simple pattern, actually. And it's very popular as well. I think it was Netflix who popularized it a lot in their Hystrix library. But actually, you have it at home as well. That is, if you have electricity at home, and I assume you all have, then you have this pattern at home as well, but it's not implemented using code. And the pattern is actually quite simple. The circuit breaker starts in closed state, which means that if a request comes in, it will just execute the request. Nothing too special there. And each successful call will keep the system in its closed state. There might be a failure. And if you configure a threshold, then a failure might not change the state of the circuit breaker. So you can say, for example, okay, I can tolerate 1 or 2 failures within a certain time span, so I'll just stay in closed state. But if too many failures happen, so either because you exceed the threshold or because you didn't have a threshold at all, your system moves, your circuit breaker moves to the open state. And in the open state, no call will be executed. So the circuit breaker still sits there, you're performing a call, and the circuit breaker says, oh, no, I'm open. I'm not going to execute your call. So every call is immediately returned back to sender with some kind of a message or an exception. Circuit breaker is open, I'm not performing your call. Okay, that's great, but then we can't stay there forever. We need to get back eventually to the closed state. So after a while, the circuit breaker will tolerate 1 call, and it will actually execute it. That's this one. It's called the reset, and after the reset, the circuit breaker is in half-open state. Half-open means that this 1 call is allowed to go through, and all other calls will still be blocked. And this one call is like the canary in the coal mine. You let it in, and you hope it will come back alive. If it does come back alive, we have a success. And the circuit breaker can move back to the closed state where all calls will be executed. And if your canary does not come back alive, or doesn't come back at all, most likely, the circuit breaker will go back to the open state again. Now, if we apply this pattern, we can say before we contact one insurance company, we need this circuit breaker for every insurance company, and we'll just assume it's closed, and then if we have too many failures, we will assume that they are, well, I don't know, doing a deployment, or they have network issues, or they have some kind of general failures, I don't know. But either way, we will not contact them for some time. We will give them the time to restore normal operations. And once these normal operations have been restored, well, we don't know when that is, but we can detect that by letting one canary fly into the coal mine and hope that it will come back to us. And if that happens, we can restore normal service operations and just execute calls to their system. And now that we also have this pattern, we have all the properties for our solution, for our routing engine that we needed to have a truly responsive system that will stay responsive even if we have quite a lot of work to do, or even if we have enormous amounts of work to do. Well, as I said, this talk is about software engineering and architecture, and until now we have mostly been talking about architecture, and there was no code yet. But this is a developer conference, so we need to have some code, don't we? So let's start with a simple thing. How do you initiate such a timeout? We use the Scala language and the akka toolkit as an implementation of this actor model. There are more implementations, but this one felt naturally for us. It runs on the JVM as well. We do know Scala quite already, so well, using this toolkit was for us the most obvious way to implement it. And this is how you do it in Scala. Just to be sure, you can write it in Java as well, if you wish. There are two disadvantages of that. The first one is that it doesn't fit on this slide, because you need a lot more code if you do it in Java. And the second one is that your hands get tired because of all the typing. If you have the Lightband courses on Akka, and you do the Scala version, your trainer will most likely tell you something like, well, be glad that you have the Scala version, because if we do the Java version, we need 1 day longer just to walk through all the code examples. It's much more verbose in Java. So let's look at the Scala version. The first thing is that we create a new actor there. We give it some kind of a name using a variable that says that's a unique identifier for this request. And that gives us the actor. Next is we send it some kind of a message. It's done using the tell operator, which you can also invoke by the exclamation mark. That's one of the Scala thingies. You either love it or you hate it. I love it. It's really short, and it's, well, it matches my view of what I'm doing. I'm telling it something. Go do it. So I'm creating this retrieve all policy data message with some kind of a code in it, and I'm telling that to the actor. And then I'm scheduling to be executed once after 2 seconds, this block of code, and it says the retrieval timeout, send that message to myself. So that's the loop arrow in the diagram that we saw, and we're just sending the message to ourselves back, but only after 2 seconds. Okay, then something more difficult. How do we contact one insurance company and get some data from them? Well, we create an HTTP request using a post method, some kind of URL that we got from configuration, and some kind of request entity, which is just the request body that's to be sent. And well, the convention was that we should send it over HTTP post, so that's why post. It's not really a choice there. And then we did HTTP, that's the HTTP client, that will do the blocking network call for us. question mark request. Why no exclamation mark? Why a question mark? A question mark is another operation on an actor, and it says ask. Not tell, but ask. So I'm sending a message and I'm expecting some kind of a response back from you. And since we don't want to wait for that, the response will come in as a message itself as well. So if we have this response message, we can get the entity from it. We can try to interpret that as response data. That's just a class that we wrote ourselves that matches the exact structure. And then we try to match that. And this is a pattern from Scala as well. It's called pattern matching. It's a pattern. It's called pattern matching. And what it says is evaluate the result of this statement. It will give an either. That's a type in Scala, either. It's a bit like Java optional. But it can actually be two things. It can be either this or that. And as you see, they have modeled it as a left and a right. So it's either a failure or it's some kind of data. If it's a failure, that's the left side of the either. That's, that you look that up in the documentation. You don't remind that for yourself. You send the failure to the client. And if it's some kind of data, then you can, you might do some post-processing, but I skipped that here. And eventually send the processed data back to our client. And this is a way of dealing with messages that you see quite a lot in Akka solutions, where you don't exactly know what you'll get, but it will most likely be either this or that, and then you can use this either type. Okay, great, but as I said, we needed a circuit breaker to make sure that we will not send unnecessary requests. Well, first of all, we need a kind of a circuit breaker, and the good news is, it's there in Akka. This is already implemented for you, so you don't have to write this, that pattern yourself and test it and I don't know what. You can just reuse that from the toolkit. And you tell it some configuration options, like I'm allowing 5 failures before I want the circuit breaker to open up. I have a timeout of 5 seconds, so I'm waiting 5 seconds before I consider something a failure, and the reset will occur after 1 minute. I've hard-coded them here, but in a real world, you would obviously read these data from a configuration file or something. Now, if we want to send a request, the first line is the same. We just send the we just create the request message, and then we say circuit breaker with circuit breaker. And then we have the same line, HTTP ask request, pipe to self. And you might say pipe to self, why is that? Because this ask did already make sure that we would get the response back, right? Yes, but the circuit breaker will also send messages. For example, if the circuit breaker is open and the call is not executed, then the circuit breaker will tell you that using a message. And this last line makes sure that this message will arrive at you at this current actor as well, because otherwise it might go somewhere else, and we would not know that the circuit breaker was open. So we asked ourselves this question again, will it break? We had the exact same script. We didn't change the line of that. You have to believe me, because I am not showing you a div there. But this time the report looked a lot better. First of all, we have no failures. I like that already now. We have no failures. As we can see, quite a number of calls was pretty quick, under 800 milliseconds. Well, a little less of the calls were between 800 and 1200 milliseconds. And the biggest amount was more than 1200 milliseconds. As I said, we had a timeout of 2 seconds. So I'm actually expecting that this bar will be bigger than 1200, but no more than 2000. That's what the timeout was for, after all. And as I also said, these dummy insurance companies would have response times varying between 0 and 1 second. And we can see that here, most of the calls are somewhere there, because if I add up these two bars, I might get well, even beyond that bar. Okay, that looks good. Now we will look at the second part of the report, and we can see that the response times are clearly cut off there at the 2-second line. So our timeout is definitely working. We have not a single call that took more than 2 seconds. Well, that's pretty cool if you have lots of traffic, and you can guarantee that you will always respond within 2 seconds. It's not always the response that somebody wanted, but that would then be caused by external systems and not by your system. We can also see that the number of users over the time that the script ran is pretty stable. And if you recall the first report, it went up pretty quick because everyone was waiting for each other. And we don't see that now anymore. But at the end of the day, this is still a bit of, I, Barack Obama, approved this message because we wrote our own script and we tested our own system. Luckily enough, we had another company that would also test the system and would actually test the system as a whole, so including all the routing engines and stuff. And they came with this report. In this report, you can see the blue line, which is the number of users. You can see the response times, and the red line is errors. And this test was designated to make the system break. So they started with 0 users, and they added users, and they kept on adding users because they wanted to find the point where it would break. And at this point, they were at 5 times the load that was requested by the client. And they gave up. This is no fun. We can't make it break. Well, when I saw this, I cried. I was so happy. Because this was actually the proof that the things that we envisioned, that they worked. We were really happy with this, and they asked us in an informal session, yeah, you're running this whole thing in the cloud. We're not yet really familiar with the cloud. Will you? We know that you can scale up in the cloud, so you can add more computers if it's busy. When did you do that? Because we didn't see really a pattern where we expected it. And we said we didn't scale up yet. This was all the initial setup. And they found it hard to believe that, but yeah, that's how it was. Anyway, before you leave, there's a couple of things that I would like you to take away if you ever face problems like these. First of all, the Reactor model, which enables you to build resilient solutions that can really face failure and still keep on running smoothly. And this Reactor model is also very suitable if you have enormous amounts of work that has to be done concurrently, but there's also a blocking part in it, like this network calls being done. Secondly, think outside the box. As I said, we started with something, building something in Spring Boot because we know it. And although that's a good start, it doesn't always get you the solution that you need. And sometimes the solution to your problem is outside the context where your problem lies. And last but not least, use a whiteboard. If you recall the solution diagram with all these actors and all these messages flying around, you can never build such a diagram right in PowerPoint. And if you try to do that, you spend a lot of time cursing PowerPoint or whichever tool you use because I need this box over there, and just use a whiteboard. Pick a marker and a wiper. It doesn't, oh, it's not correct. Well, you wipe it out, you draw it again. It's so much quicker than doing this on a computer directly. And obviously, you can digitalize it afterwards, but start with a white box. That's it for me. If you have any questions, feel free to ask. I think there's a microphone.
I was wondering about the fine-tuning of the ACA model. I think you said that you didn't need to scale it up or to fine-tune it, but I was wondering if you had to tune the ACA system for giving the number of instances or something like that, and how did it went?
Actually, we did not need that. That's more or less the boring answer. But we just started with the sane defaults. At least we assumed they would be sane, and well, a quick scan revealed no things that we would worried about. And we figured that it would be easier to just start with defaults and see where that happens, where that brings us, than starting to do a heavy customization up front without knowing whether we would actually need that, because all customizations need to be maintained, and you need to document why you made a certain decision and why you do that and how you did it. So we started with no customizations, and that turned out to give a very good solution already. So yeah, no need for that.
Okay, and how about location transparency? Did you use multiple nodes or just a single node surface?
During the tests that we performed ourselves, we had just a single node on an Azure, well, on a relatively small Azure box. I don't know the exact specs anymore. With the external test, we had 2 instances and an Azure load balancer in front of it, just to be sure, because in a real production environment, you're almost never running a single system, a single node system for this kind of scale. So that was with a load balancer in between and 2 nodes.
Okay, but did you need to use ACA with location transparency for that directly, or did you use the load balancer just to? So you did use the load balancer just to split the traffic between different nodes. You didn't use the ACA directly for that, for location transparency of the actors.
Yeah. Yes, you could. We used the load balancer to just split the load. You could use ACA remoting for the location transparency that I mentioned in the Reactive Manifesto. But in fact, we decided not to use that. Yes, it's possible, but it makes things a lot more complex. Working with remote actors, I once tried it, involves a lot more error handling, because you need to do some kind of a lookup to your external actor that might or might not live somewhere else in the cluster. And that overhead is pretty big. And since we had this since we have no state in this routing engine, it just gets in a request. It sends out other requests, it assembles the responses, and it sends it back, but there's no state other than that. We decided that, well, since it's almost stateless, we don't actually need to distribute the state over the cluster. We don't even need to form a cluster. And that's how we ended up with actually not using the location transparency in this case, but you could do that indeed.
Okay, thank you.
You're welcome.
So I had a question about, you mentioned that in the Netherlands, for example, most people have like 6 or 7 policies. So when such a user logs in, isn't the problem limited to just accessing those 7 companies instead of 400?
Yes, if you're the only user of the system.
Yeah.
But there are 7 million households in the Netherlands and around 17 million people. Let's assume that 10 million of them are somehow of the age that they might be interested in this kind of stuff. You're not the only user. And the challenge for us was in having this enormous amount of backend systems and not knowing upfront which one we would need at a certain moment in time.
Yeah, so you did testing for 400, but you knew before that in a user scenario you would just do 7 or something.
Yes,
within the session.
One specific user might even need just 2 of them.
Yeah.
But at the same moment in time, there might be, I don't know, thousands or maybe millions of other users needing another subset of those 400, and that's where the real challenge lies.
So, and I was also wondering, how do you communicate to the user that one of these companies isn't having a response? So they are down, their service is down. Do you tell them to call them, or what do you present to the user?
We, if I recall correctly, we have a very non-informative error message, something like, well, there's a temporal error, just try again in a few minutes, something like that, because you don't always know what happened. And even if you do know, you might not want to tell the user because it's way too detailed for them. This system is targeted at end users that have little or no IT experience. And it doesn't mean anything to them if I say it's a failure because it took 5 seconds, or it's a failure because the protocol wasn't respected. They don't know the difference and they don't care. All they see is, I have no data.
Or maybe you could tell them like, okay, we know you have a car insurance, but we can't get the details of your car insurance.
Exactly,
right
that's what we do. We can say something like, you have a policy at this company, but we have no details of it.
Okay.
We just know that you have it. If not, then I would like to thank you for your attention, and I hope you all have a nice day today with a lot more interesting sessions. Thank you.